As you have heard, we are going to record this session. So please, if you want to get this session afterwards, we can email it to you, or we can email you the link to you. If you have any questions, please just put the questions into the chat. This afternoon, maybe you go to the first slide, please. We are.
Excuse me, just sorry, Richard.
Okay, no problem.
There we go.
This afternoon, we have a complete and secure visibility in OT and IT networks. Together with Garland, I have here Ross Green, responsible for sales in Europe, and Neil Wilkins, the technical head of Europe from Garland, based in the UK. And Ross and Neil will going to do the presentations. So if there's any questions, please put it in the chat, and we are going to answer it after the presentation. Yeah. So, and I say very welcome from Akayo from our side. Thank you very much. So now the stage is yours.
Thank you, Richard. Thank you, Akayo, for this opportunity to present complete and secure visibility in OT and IT networks. Next slide, please, Neil. Before we start, for those not familiar with Garland Technology, I will just provide a short one-slide introduction. Garland Technology are a US manufacturer of network visibility products. We were established in 2011. We are a privately owned company headquartered in Buffalo, New York, with our manufacturing in Rochester, which is near Dallas, Texas, USA. Our customer base is worldwide, with solutions deployed in pretty much every vertical sector. Next slide, please, Neil. The network and the data transferred over it is the lifeblood of any organization. Access to and the performance of a company's applications are totally reliant upon it. Without network visibility, then an organization is blind to potential threats and performance constraints. Next slide, please, Neil. So what can network visibility provide? It provides awareness of all the devices connected to the network and all data flowing across the network and also into the network. The benefits include it provides an organization with the data and metrics to improve network and application performance. Access to the network data is an invaluable tool when troubleshooting issues, enabling problems to be resolved much faster. As well as performance and troubleshooting benefits, network visibility is the platform for improved security. It allows security tools to recognize the baseline and then identify anomalies. It also provides the basis for obtaining and then storing data required for historical look-back analysis following a breach and satisfying regulatory requirements. It also provides the necessary data for future expansion and business transformation plans within an organization. Quite simply, without network visibility, an organization is blind. Next slide, please, Neil. Most organizations have recognized the need for network visibility. However, many accept that their current implementation is not sufficient. In this survey by Vance and Bourne, 500 IT and security decision makers in organizations of over 1,000 employees were asked questions relating to network visibility. Of these respondents, 300 were from Europe, with a total of 100 in Germany. As you can read here, 2/3 see network blind spots as one of their biggest challenges when protecting data. Nearly 40% lack a strategy to identify and respond to a security breach. and 3/4 agreed that they needed to improve their network visibility in order to make their network security more effective. Next slide, please. Oh. When we talk about network visibility, you will often hear the term network visibility fabric. This fabric is effectively a secure network of devices that provide network visibility. There are two components of this fabric. The part we are looking at today is the out-of-band infrastructure. This provides packet level visibility of the network. It is totally invisible to the network, non-disruptive to the network, doesn't impact the flow of data on the network, and most importantly, a totally secure method of mirroring packets from locations across a network and delivering them to security and monitoring tools. The other component of a network visibility fabric, which we're not covering today, is for the management of inline tools such as next-gen firewalls, IPSs, decryption and encryption devices, etc. This inline infrastructure provides the network, protects the network from tool failures and provides the mechanism to improve their performance, manageability, and resilience. So let's now look at the out-of-band elements of a network visibility fabric. On the left of the slide, you can see a customer network. Just hit the next button, Neil. To mirror the data from this network, a customer can use span or mirror ports on switches and routers. And then we also have network taps. These are physical devices that are installed between network devices, or they can be virtual taps that are installed within virtual machines. Taps mirror the traffic, and unlike span ports, are able to guarantee viewing 100% of the packets without impacting the timing of those packets. Span ports were originally implemented when switches, within switches as a mechanism for troubleshooting a switch or a router. They were never intended to be a constant security monitoring point, and therefore are not the method of choice for a security conscious organization. In reality, most enterprise customers will elect for a combination of both taps and span ports, tapping the critical links and using span elsewhere. All of these mirrored data feeds must then be delivered to the security and network monitoring tools. This data is therefore aggregated together and then shaped and directed by the use of a network packet broker to the tools. Next, hit the button again, please. Now, a consideration that is sometimes ignored is that this communication of mirrored data to the tools must be one way, i.e. what we call data diode. There should be no access through the visibility fabric back into the live network. And this is an area where customers need to be aware of the vulnerability that could be exposed through using span ports, as they physically can be used to receive data as well as mirroring data out. There is a reliance here that the span ports are configured correctly. Next slide, please. So that's my basic introduction into network visibility. I'm going to hand over now to Neil, who's going to take you through some of the products and also some solutions using those products. Thank you, Neil.
Thanks, Ross, and thank you for that very good explanation of why we should be using secure simplex communication, as we call it, data diode. So when we, as Ross has said earlier on, we're only going to be looking at inline tool, inbound at the moment, not out of band, sorry, not inline tools today. So if we take tap network and we're looking at it at out of band, we have effectively 3 different modes of operation. The typical way that you see a tap work is in breakout mode. So on the left-hand side of the slide here, we have a router to switch and switch to router communication, east-west to west-east communication, coming through the A to B port and flowing back from the B to A port. In a typical breakout mode, that data is sent out of 2 ports to the C and D port. So you have 2 links, both at full duplex coming through. The second mode that a tap is very frequently used at is aggregation mode. And aggregation mode is used very, very frequently in an OT network as opposed to an IT network. So as opposed to the data coming back to both the C and the D port, just the single stream, we're now aggregating both sets of data out of the C port and the D port. This gives you the advantage of being able to put 2 devices in there, but often in a OT network, it is done for the purpose that our links are very slow. So we're often using slower speed links and then pulling up into a higher speed link with the C and D. And the third mode that you'll see is called regeneration, often also called span mode as well, where we're taking the data directly in from a switch, adding and bringing that into what would be the A port, then reconfiguring those taps to be the B, C, and D port, all getting copies of that original data coming out. Now, I should say in a lot of instances, taps can be configured into most of those modes. Then on top of all of that, you can then, I'm going to say, protect your monitoring tools and your security tools. There is the option of also adding a level of filtering at level 2, 3, and 4 on top of a tap, so that we can now start limiting the data sent to the monitoring tool or the security tool. And we can do that in both out-of-band and inline modes. A way that frequently we also use taps is a media conversion. And in fact, just earlier on today, somebody asked me, can I bring from copper to fiber? And most definitely you can. In taps, we have taps that have just about every different interface that you want on them. So we can have fiber with copper monitoring ports. We can have copper ports with fiber monitoring on the side of them. And we can do conversion from different sorts of fiber as well. One thing you should remember, of course, if you use, as put on the slide here, that we have SFP pluses, if you put those on the network side of things, you cannot guarantee fail-safe. And fail-safe is where when you lose complete power, your network is remade and reconnected. And typically that's in the region of about 27 microseconds that comes through. So when we come back to what Ross was mentioning about secure simplex mirroring or data diode, network taps have no MAC address that can be accessed at all through the network ports. Data diode taps can guarantee that no data can ever be injected into the monitored network. And that's something Ross touched on and is very important. If we look in many of our OT networks, when they come to be with a utilities provider, there is a regulator that overrides those utilities providers and rules them. And the regulators often insist that data cannot be induced back into the network. And a data diode or a simplex tap is the only way to ensure that you cannot put things through. Span and mirror ports on switches can receive as well as transmit. In a lot of older span ports, mirror ports, you can't reconfigure that. On some newer port switches, you can configure that, but there is always the tendency for some form of human error that, again, you have to provide the regulator with proof that you cannot get through this. So we use data diode taps in a lot of ways. A data diode network tap, we do not let the data ingress back into the tap on that C and D port. So if you remember our original diagram, the data from router to switch and switch to router, the data came out of both the C and D port. In a data diode network tap, we do not let that data ingress back into that way round. And on a span port, it's exactly the same concept. The data will not comply back into the network, and we cannot physically allow that data back into the network. And that is very, very important in industrial plants, where we're stopping the link from the control center back, so we cannot bring and induce data directly back into our network again. How do we do that? Well, with passive fiber taps, our splicing technology blocks all incoming data, light coming back in on the monitoring port effectively. So we're stopping the light coming back in to the monitoring port. So again, we can say that we're not injecting traffic back. On passive copper ports, we have no physical receive connection. We don't connect the receive back up to the PHY. So the PHY is left empty and we cannot receive back. There are ports as well that are active copper and fiber. The monitor ports here, again, we do not have a physical connection back in again. So it's impossible to bring data back. There is an exception to this rule, and Ross mentioned earlier, we're not going to be talking about inline taps. Bypass taps, inline taps, you cannot do that, so you still have that capability. So if it's a tap from Garland, which is a bypass tap, that does not have the data diode capability in it. But in the simplest way, what we're doing is we are not connecting the receive back up, so we can't induce data back inside the network. And the third part of this is we have a virtual tap as well. Our virtual tap has been designed with the concept in mind that you cannot induce data back into your network again. So we have a virtual tap that is hypervisor independent. We run on any we do not touch and go near the hypervisor. So you can be, whether you're on Amazon, whether you're on Azure, wherever, it makes no difference to us. We have support for Windows Server 2019, Linux support via Docker, and we have native Linux support in Red Hat, Ubuntu, and SUSE. Now, we again guarantee that there is no incoming traffic. And this again came out of a regulator requirement in a large power generation company. So we designed our virtual tap to be very simplistic in its way of use, and to as much as possible emulate an out-of-band physical tap. So normally with a virtual tap, most manufacturers create a VXLAN tunnel out to the end monitoring station. If you remember Ross's very first slide, if you create a VXLAN tunnel, you're not typically ARP, and you send that ARP out to the end station with whatever it is, an end device, and create a reverse ARP. Then through your packet brokers, you're having to create a reverse string back in to make that bi-directional traffic. Within our virtual tap, we have configured it so that we static ARP inside the same chassis, and effectively you can put any address in that you want at the end of the day. You have one or two configurations to do, you put anything there. And the only reason we're using the VXLAN tunnel is to take the use of the IP stack that already exists inside your system in case you have jumbo frames or whatever and you need to fragment, and we use the VXLAN to fragment the link. So we create a link directly, we send the data out of a second port, a second mirroring port, and send it directly onto the network, the same as we would with a physical tap, and we connect to the packet broker with no reverse link, making it again a simplex functionality. So network packet brokers are the next part of this equation. And I look at those as the device that manipulates and shapes the traffic and presents it to the tool in the way and means that you want it to be. So The concept of a network packet broker is to reduce the cost and complexity. It allows you to do multiple speeds, multiple ways. It allows you to detect breaches much faster. So you can use a single tool connected to various parts inside your network, aggregating the traffic and bringing it back. It also means we can reduce the burden on one or more security tools. We can filter traffic to one tool. We can load balance the traffic to another tool. And we can extend the life of a monitoring tool. So we may well load balance multiple ports at lower speeds to a single monitoring tool. And again, because you configure a packet broker for ingress and egress ports, we support the regulatory compliance because we're not asking for the data to come back from the tool directly back into the network. It's not the way you would normally configure a packet broker, and you'd have to go specifically out of your way to want to do that. So we look at packet brokers as having a very layered functionality. Our live network is doing whatever we have with our data. We have a span and tap layer inside it. And in fairness to most networks are a combination of both span monitoring and tap layers between that. We aggregate that data from multiple different tools to multiple different taps and places to multiple different aggregation devices. So for forensics, for IDS, for analyzing things. And then we have a third layer behind that, which we class as the advanced features layer. And I'll explain that just a little bit second. So our first layer, span and tap, is bring everything in. We aggregate it together and hand it out to multiple tools. And then the advanced features layer is really how we start to manipulate and present that traffic to the correct tool in the format that you want it to be. So from my perspective, the aggregation layer does aggregation and regeneration from many to many, one to one, many numbers to many numbers. It allows me to filter at layers 2, layer 3, and layer 4. And it gives me some simple levels of load balancing. Again, it gives me the option to decapsulate traffic. It gives me whether it will be GRE, VXLAN, MPLS, VLAN traffic. It allows me to tag and strip VLANs, and it allows me to encapsulate at GRE and VXLAN tunnels. But as I go further up, I start to want to do more and more. And that's where we as Garland put in our advanced features layer. So in the advanced features layer, I'm starting to look at packet slicing. So typically we all have encrypted traffic, whether that be TLS traffic with HTTPS, whether that be encrypted traffic for whatever we're passing through. I can't always see that traffic and don't need to. So I slice the traffic, remove the data, and just keep the headers. So I send the headers to the tool. And I have flexibility of how much I could do in between there. I then may also want to timestamp that data coming in and out. So I can use time stamping and stamp that data as well. When we have a layer of a network that gets larger, then I tend to have both. As I mentioned earlier, I have tapped links, I have span links, and I probably have links from the virtual links as well. Once I start to get that, I'm going to have data at least twice somewhere in my network. And that's where the deduplication layer comes in, and I can start to deduplicate and take the second packet out of the network. I would also then be using metadata. I can be using a metadata engine, so I can be doing IP and net flow IP fix and net flow generation. And then some of my filtering could be more in terms of session aware filtering, and I can create user defined filters. So in some instances, I want to look directly inside my payload because it could be carrying another payload inside there, you know, things like WhatsApp traffic and things inside, and I want to get there and start to filter that traffic out. Some packet brokers do actually use decryption, can decrypt SSL decryption. From our perspective in Garland, we don't do that. We feel that whilst decryption is in itself fairly easy, the key discovery is quite a complex thing to do, and you're adding that overhead inside a packet broker and that additional cost inside. So we always partner with somebody for there. And then the last part is something that we have quite a bit of now. It's an integrated tap and packet broker. So in a lot of edge situations and a lot of finance institutions, we have an integrated number of taps inside a packet broker. And we have different options for that, but commonly they are used for in-time tool connectivity. And this way I can serial chain, use a heartbeat to make decisions about what is going to happen if one inline tool is removed from the network and another one, should I take a pair out if they were encryptors and decryptors, and how I then do load balancing of whether I have active standby tools and how I run those tools. That again, we put in what we call an advanced features layer on a packet broker. So at the normal level, I have simple aggregation, and at the higher level, I have that aggregation where I can manipulate the data more and more. So let's have a look at how we've put these in place into a number of customer solutions and a customer way of doing things. So this is an OT customer of ours. It's a large customer in manufacturing. They have manufacturing worldwide. And this is actually a fairly typical solution. The customer has centered on an IDS solution, and they need to have visibility at all levels within their manufacturing plant. So if we look at the very low level, level 0 and level 1, very frequently in manufacturing, what we're now doing is tapping at that level between the PLCs and the remote terminal units. So we tap down at that low level so that we can see the data that's coming in there. We often also tap at the level above that at the control system level. So this particular customer themselves wants to see what is happening in one part of his plant, and he wants to be able to see what is going on at the workstation level that are controlling the PLCs. So he actually needs to see the specific change that is happening and log that change. So we actually tap there at both the PLC level, so we know what's going on at that level, and we also tap at the controller level above that so that we can see there. At his remote plants, at other plants, he doesn't want that level of granularity. So we use an aggregator tap, and we use this form of aggregator tap very, very frequently in an OT environment that will allow me to use the span ports of the switch, and I'm coming into at the switch level there, and then I go upwards in a fiber link to a packet broker in the backbone. And the same instance back up to the packet broker from the main plant as well. Now, the next problem we have in a lot of companies now is they're starting to look at, one of the things I always say to people is, where is the flow? If we can see the flow of your data and the flow of the traffic, that's what we need to tap, and that's where we need to come into. And in this instance, the customer is also using data diode taps. that come after their firewall and before they go into their IT environment. So they can actually start to see now what's coming through, analyze what's coming through, and make the decisions of if the firewall, one, configured correctly, and two, are any problems likely to be coming in from the enterprise side of things rather than the OT side of things. So the benefit with this particular customer, he has a very simple implementation. He has data diode capability everywhere, and we've eliminated just about every blind spot inside the network, and we've completely taken that at a very simple, very, very easy to configure network. This is another OT environment, and this is actually a utility provider, a European utility provider. And the black box that you see here is something that was in the actual Nova network as well. That black box can actually be 4 taps or 8 span ports. And then with this particular utility provider, who also has an IDS solution, we have aggregated the span ports on his switches, because these are very low speed switches, by the way, and we've aggregated those span ports out into that single tap aggregation tap. What we've actually done is we've taken 4 switches up of 1 F uplink. You'll notice that box has 2 uplinks. We've taken 4 switches to one of the uplinks and the other 4 switches to the other uplink. So we've done that in 3 locations throughout of his utility plant. These are a water-based utility, actually. We've taken that out in 3 different locations. We've pulled those switches back and we've aggregated that. We've taken them over a fiber link to a very small network aggregator. So a very small packet broker, that we would say just the aggregation level packet broker. We are actually, for that customer, tagging his VLANs, his switches, so that he knows, tagging his taps rather, the uplink, so he knows where they've come from. And we're sending that on to the IDS. And he's managed to come away with that with a very low cost IDS platform. The link to the IDS is 10 gig, and the link from the taps are just 1 gig links brought upwards. This is actually some form of carry on from the same customer who is a utility. So now at the top level of this diagram, what we've done is we have passive 100 meg taps. And we're using that 100 meg tap to tap between multiple switches, and we're aggregating that back up again to that same device. Now, the difference this time round is those, as you say, we've got these passive taps that are very fail-safe. They've got data diode capability in them, and we're bringing them up to the aggregation tap. But here we're only using one of the uplinks. And as I mentioned earlier on, we often use a tap as a media converter. We have a very small portable tap that can take its power off the mains, or it can take its power off the device that's connected to it. That is the size of an iPhone 12 mini. It's exactly the same size as that. And we're bringing that out from the central black tap there on multi-mode fiber, and we're using the mini tap as a media converter. And we're monitoring with the IDS on the USB port. So we're monitoring remotely over a multi-mode link from this one plant and one water plant, and taking the tap out as the media converter at a low speed and a longer distance. We also have versions of that can do exactly the same in a 10 gig side of things. So the benefit we have for the customer is a very, very highly reliable passive solution that does that media conversion for him. And the point is that we'll have no loss of data or no packet loss in the networking at all. This is a much more complex environment now. This particular environment is a large energy provider, and there is at the start no security. So there is complete security inside this energy provider now. This is a big use of virtual taps, and in substations they have virtual taps that are monitoring the systems controlling the flow, the power, the valve status, etc. We also have physical taps in the substations as well to tap the physical links. We then aggregate that link directly and send it out over a VXLAN tunnel over a private cloud to a data center. Also, as shown in the bottom part of the substation, we have bypass taps for the firewalls as well. So the firewall is connected to a bypass tap, or more than one actually, in an active mode, to give the customer the opportunity to manage his firewall as an inline appliance, have a second firewall by the side of it. He can do sandboxing, he can change his software, he can move it in by keeping his network live and bringing one in. So all of those substations come back in to a master data center. In fact, it's, for simplicity, it's shown as a master data center here, but there is more than one data center. There's a master and there's a backup data center. And we aggregate the traffic from the substations over a VXLAN tunnel to the master data center, where all of the security tools are there and all the storage of everything is going on. So it's duplicated around multiple different sizes of substation, where we're doing both active and passive tapping, as in by that I mean VTaps, virtual taps, to see what's going on inside the servers, and physical taps to see what's coming on the network. So we have now had a system that the regulator for that country is happy with. We can create a single unidirectional system that takes data from substations all the way back to 2 monitoring stations centralized inside a country. I think the last example I have here is actually, it's quite an interesting example. It's a large insurance company. It's a very large worldwide insurance company that uses Cisco Meraki switches for their wireless environment. And they, of course, have a multi-location IDS. The IDS is worldwide again. But the problem that they ran into, and something they didn't notice on very early days, is that they thought that when they use the Meraki device, they would connect the span or monitoring part directly to their forensic tool, to their IDS tool. It soon became clear to them there is limited capability inside that span port. So the span port itself only sees the core in the Meraki stack. So you can stack their accesses back to a core. So they can only see the core. They cannot see the data that flows between their access stacks. So they were limited to 20% of the data. Whatever was going in at access level from floor to floor or whatever was not seen as data. So from this instance, what we had to do was tap into the access stacks and also come into the core stack So we used the combination of the core stack of our aggregator that has integral taps. So we could access him with 4 integral taps into the core stack and into their routers. So we could tap between the router and their core stack. And then at the same time, we used our passive fiber taps to come in at the access level to come in that way. Brought that all back to the same aggregation device, and then brought our forensics tool out there. Now, this way we could see, we actually used a lot less rack space than was required, because we had taps that were integrated into the packet broker, and we also had standalone taps that were 1 rack mounted. We managed to see now 100% visibility rather than probably 20–25% of what was going on their network. That allowed them also to use much smaller IDS platforms than they were going to use elsewhere as well, because we could use a much smaller product, we could filter through, and we could do a lot of load balancing without having to put such high part on there. And from our perspective, across their whole of their insurance company worldwide, they could standardize then, of course, on their core Meriaki for wireless communication, and then us as a form of aggregation tap to allow them to come into everywhere. So from our perspective, we will help you do anything. So if you have any form of issue and problem, I'm 100% certain there isn't any sort of network that we can't tap into, but we will both ourselves and our partners will help you design whatever sort of proposal you need for whatever challenge you have. We'll whiteboard drawings with them, we'll create Visio diagrams for you, and we'll frequently do product demos. We'll frequently do product demos for customers and for end users, usually on the simplicity and ease of setting things up for you. So really that's where the end of I've come to today. I guess the thing now is to open back up to Bert and ask if there are any questions that want to come back through, Bert.
Okay, thank you, Neil. I think this was very informative. So if someone has questions, please put it in the chat. At the moment, I have only one question. The question is, can I reduce the bandwidth to one special monitoring tool because it has only a special capacity on this?
Yes, you can, Bert. You can. So depending on how you want to do it, you can do it in multiple ways, to be fair. You could filter your traffic with a tap and filter what you want. So you've limited the bandwidth to that tool, and you can do that. And customers quite frequently do that. Or if you have multiple locations, you can do exactly the same with a greater degree in a packet broker. So you could do that probably more granular inside a packet broker, and you can limit the amount of data that is going to that end monitoring tool. You can also load balance some traffic through to it as well, if that's what you want to do, and specifically load it to one direction or another.
Okay, thank you. Your presentation was so clear that there are no other questions at the moment. So if you still have any questions, please come back to us and send us an email, or go to our website, or go to Garland's website and send us, reach us via LinkedIn or whatever. There's another question now coming up. What's the difference between span and tap layer versus aggregation layer?
So at the span and tap layer, so if you take that very simple layer, that is the area that you're going to have to come into your network. So that is where you decide. The way I look at it is, let's look at the way our data is flowing, and that is where we're going to tap into the network. And we could be doing that in multiple places. Now, if we do that in multiple places, you would need multiple monitoring tools. So the aggregation layer is a device that brings all of those links back together, and you can monitor from one specific location. Or if you're having, say, two different sorts of forensic tools, you can send the data to those two forensic tools in one location. So the aggregation layer really is saving you money on your monitoring tools, your security tools, your forensic tools.
Yeah, I think just to add to that a little bit, Neil, the aggregation layer also includes regeneration. So at that layer, you're also able to take the traffic from multiple locations and then direct it to multiple other locations. So if you have more than one tool, so if you have an IDS and a deep packet inspection tool and maybe Wireshark or what have you, you can direct the same traffic or different traffic to each of those tools. So it gives you the ability to share that traffic to multiple tools as well.
Thanks, Ross.
Okay, thank you. Yeah, I think the aggregation is a quite common use case because the customers want to have more locations and put the traffic into a central location.
Yeah.
Okay.
One other thing that perhaps to mention there, Richard, is that the span/tap layer. That's the layer that we're obtaining the data. So and they're just two different methods of obtaining the mirrored data, and they are different approaches. A tap is a physical device that you put in a link, and you can guarantee that you're going to see 100% of the data, whereas a span port is a port that's configured on a switch. And in that instance, you're not guaranteed you will see 100% of the data because it has the lowest priority within the switch, and it's possible to oversubscribe a span port on a switch. So, they are different approaches. For anyone that's 100% security conscious, then they would use taps rather than simply span ports.
Okay, thank you. The last question was if they could get this, wonderful slides, that original tone. So of course you can get this wonderful slides from wonderful Garland, from the wonderful distributor Acquire. Okay. Thank you very much for everybody to listen to us, and thank you Neil and Ross for presenting, and I wish everyone a nice evening. Thank you and goodbye.